We can use group theory to determine the molecular orbital diagram of more complicated molecules that contain more than just two atoms. Consider a water molecule, for example, which is a relatively simple example with which to begin our group theory approach to molecular orbital diagrams. We can do this in one of two ways. One of them is by inspection, and the other is via what is called the projection operator method. The projection operator method is very similar to the approach that we've taken to determine vibrational modes of molecules, where you treat the x, y, and z axes of every atom as vectors with which you can generate reducible representations for potential orbitals. And this is useful because the p orbitals, for example, lie along the x, y, and z axis, which allow us to generate reducible representations for sigma bonds and pi bonds and things like that. And as you'll see, sometimes it's easier to instead do what's called the method of inspection. So let's take water as an example and go through this in two different ways. So when we create molecular orbital diagrams for multinuclear, non-heteronuclear, more than just diatomic species, we need to take the outer atoms and call those the group orbitals, and then apply it to the center atom by essentially when we create our molecular orbital diagram. So traditionally you have your energy on one side, and with homonuclear and heteronuclear diatomics, we would just have one atom on the left and one atom on the right. Now instead for these more than two atom molecules, we will place the center atom on one side, so that will be oxygen, and on the other side we will have our group orbitals. So typically what you might think is that you have oxygen on one side, we're looking at its valence electrons, it's got the 2s orbital and then the 2p orbitals, and hydrogen being the outer atoms, and since we have two of those, they would have 2s orbitals, and they'd both be at the same energy. Oftentimes you'll see these two orbitals that have the same energy drawn just slightly above one another just to keep things simple, or occasionally you'll see them next side by side. But either way, this is meant to depict that they are of the same energy. And then, of course, we would start with our valence electrons. So for oxygen, that's going to be 6. And for each hydrogen, there is 1. So we would place 1 electron there. All right, so how do we do this using the inspection method and the projection operator method? So for the orbitals involved in hydrogen, the only ones that we have are the 1s orbitals, which is why using this molecule as an example is so easy, because you don't need to consider any of the additional orbitals that are involved in the atoms that are beyond helium. So if we are to think of the way that these orbitals can exist on the outer atoms, they are just these two s orbitals, and if they're in the same phase, they would look like this. And if they're in opposite phases, they would instead, one of them would be unshaded and one of them would be shaded. Okay? And effectively, hydrogen only has this orbital to deal with, so this is really the only orientations that can exist. So if we were to look at the ability of these to exist in different ways, we can create our different reducible representations for these outer atoms. So we're going to have two of them, since one of them is when they're both in phase and one of them is when they're out of phase. So we'll call this 1, we'll call this 2. So this will be our reducible representation for 1 and our reducible representation for 2. For the first reducible representation, for the identity operation, everything stays in its place. So we would get a 2. Remember that the C2 axis runs up and down on this molecule, going through oxygen. And when you do a C2 rotation, notice that both of those orbitals move. So this would get a 0 for the C2, even though they would look the same because the actual orbitals are shifting. This actually gets a 0. Sigma b in the xz plane, that's the plane of the screen. If you did a mirror reflection through that, everything would stay the same and you would get a 2. And then the yz plane is the one going along the C2 principal rotation axis. So everything would flip and it gets a 0. Now looking at the second opportunity, identity gives us a 2. The C2 rotation, everything flips, so you get a 0. The sigma b and the xc, everything gets a 2. because everything stays the same, and in the YZ, very similarly, things flip, so you get a 0. And this would be our reducible representations for both of these, and now we can use the reduction formula to determine what irreducible representations make up this molecule. Now we need the character table. So we can do our reduction formula for these. Since they're the same, they're both going to have the exact same thing, so I only need one of these reducible representations. I see that the order is 4, so 1 over 4. 2 times 1 times 1 is going to give us 2. The next one is 0, so I don't need to do any math for that. 1 times 2 times 1 is 2. And then this one is also going to be 0. So that 2 plus 2 is 4 divided by 4 is equal to 1. And that tells us that there is one A1. And now if we were to do this for all the other ones, we would see that there is no A1. And because I already know this, the number of B1s, if you did it for A2, I promise you that it equals 0. And then let's do it for B1, because I know that that one is also present here. 1 times 2 times 1 plus 0 plus 1 times 2 times 1 plus 0. And again, this gives us 1 B1, which means that overall, our reducible representation is equal to 1 A1 plus 1 B1. Now this means that the only irreducible representations that we can use to create our molecular orbital diagram to create actual bonding interactions are going to come from A1 and B1. Okay, so then once you've determined that, you need to look at the center atom orbitals and see which ones apply. So don't forget that for an oxygen atom, you have access to the S, the PX, the PY, and the PZ. And we can use the character table to see which of those orbitals correspond to those orbitals on the center atom. So the top row of any character table that you're using is always going to be equal to an S orbital. They actually don't even put it in there because it is always the top row. So A1 corresponds to an S orbital on the oxygen atom. So A1 is the S orbital on an oxygen atom. I also see in the linear column that it corresponds to the z-axis, or the pz orbital. So this is both an s orbital and a pz orbital. And remember, the pz orbital looks like this, where you have one shaded region and one unshaded region. And then the B1 orbital I see has an X in the column, so I know that this corresponds to the X orbital. So B1 corresponds to the X orbital, and typically you will assign the axis that goes out as the Y, which means the X-axis would be going in this direction, which means that the PX orbital looks like this, again with one shaded region and one unshaded region. Now notice that this means that we can create a sigma bond using the A1 of the center atom and A1 from the outer atoms, in addition to using a B1 with the PX orbital and the B1 irreducible representation for the outer atoms. Now, notice that we have two options, which we said, where we could have some sort of interaction with the outer atoms with the center atom. And if we were to look and assign an irreducible representation to these, we can do so with relative ease. So remember, this is the z-axis. If we were to do an identity on this, everything would look the same. If we were to do a C2 rotation, all the molecule would look the exact same. So this would also be a 1. The sigma in the xz plane, which is the screen, everything would still look the same, so that's a 1. And then if we were to do it in the yz, everything would shift, but they would look identical. So this actually is the A1 representation. Now, if we were to do the same for this one, if I notice that at identity, everything looks the same, so that should be a 1. If I did a C2 rotation, the positive and negative phases would invert. This would be a negative 1. And if I were to do a sigma b in the xz plane, that would be a positive 1. And if I were to do a sigma b in the yz plane, that goes in between the atoms, then they would invert and they would change phase, and that would be a negative 1. And notice that that corresponds to the irreducible representation for a B1. So in fact, this shape has the irreducible representation of B1. This means that these are my group orbital interactions, and I need to identify, using the energy in addition to the symmetry, which of these group orbitals will make bonding interactions with the center atom orbitals based on their irreducible representations. And this gets to the heart of the issue, is that bonding doesn't just occur when energies are close enough. The symmetry also has to match. So now let's look at building our molecular orbital diagram using these irreducible representations. So as you just saw in the diagram that I displayed, the s orbital on oxygen is too low in energy to interact with the s orbitals of the hydrogen atoms. So therefore, even though this has the right symmetry as an A1 interaction, and you can envision an s orbital right here being able to match symmetry-wise to make a bond, because the energy difference is so great, this is actually not going to have any sort of interaction. So I'm just going to draw this straight over as a non-bonding interaction. And that is going to be also, we're going to call it the A1 irreducible representation because it corresponds to this s orbital. And I'm going to take both of those electrons and place them there. So that basically is a non-bonding interaction, NB, or non-bonding interaction. Now instead, I know that the PZ orbital is close enough in energy and has the same symmetry with which to combine to make a bonding molecular orbital here. And you can envision that overlap as looking like this p orbital with the shaded region up top interacting like this with the s orbitals. And notice that the phases match and the symmetry matches to be able to create that bonding molecular orbital. And in fact, that is what is happening. So we would take the A1 and create our first sigma bond. And don't forget, anytime you create a bonding molecular orbital, you need to also make the corresponding anti-bonding molecular orbital. And both of these are going to be A1s. So A1. All right. Now the next step is to see that the B1 bonding interaction can occur, where if you had this orbital here, where one side was shaded, and it could combine with the two outer orbitals like this. And notice that the shading and the phasing and the symmetry matches with which these two orbitals can overlap, thus creating our additional sigma bond. And again, that comes from the B1. So this overlap is going to be a little bit less because this px orbital on the center atom is jutting out, whereas this one is pointing closer to these orbitals. And that overlap is going to be just a little bit less. So you likely in your quantum mechanics class solved for the overlap, and that was the value that you were solving for. So that overlap being a little bit lower means that I'm going to make my bonding interaction a little bit less. It's still a bonding interaction. It still produces a lower energy orbital, but just slightly above the other one, which also means that our anti-bonding orbital will be slightly above. And this Millikan symbol will be a B1 for both the bonding and the anti-bonding molecular orbital. And then notice that we also had, so this was coming from the B1, we also have that remaining B2, which is the PY orbital that doesn't have any symmetry match, and therefore I'm just going to bring over its energy, and again it's going to produce a non-bonding orbital that has B2 symmetry, because that was the corresponding Millikan symbol or irreducible representation for the PY orbital. So we still have our same number of electrons. 6 plus 2 is 8, which we've already placed 2 in there. Now we'll place 2 more there. That's 4, 5, 6, 7, 8. And now notice that our molecular orbital diagram matches our Lewis structure, where you have 2 non-bonding orbitals, both located closest in energy to the corresponding atomic orbital coming from oxygen, which is why we have those 2 lone pairs. And we've created 2 sigma bonds corresponding to these 2 sigma bonds here. So this gives us our molecular orbital diagram for a water molecule. Now let's step it up in complexity just a little bit. So rather than doing the projection operator method for complicated molecules, it's easier to do it oftentimes by inspection. So when doing it by inspection, you first need to consider what the group or outer atom orbitals look like in any sort of configuration, and then assign irreducible representations to them. So the outer atoms in a CO2 molecule are oxygen, which only has access to s and p orbitals. And we can just systematically walk through each of those and see what they might look like. So the center atom will leave blank, and then draw our lines to each outer atom. And we'll start with, let's say, the px orbital. So the z-axis on a linear molecule is always the internuclear axis. the y-axis in those cases always go out at you, and so therefore the x-axis has to be going up. So two px orbitals on oxygen atoms look like this. And let's do both the configuration where the phases are aligned and the configuration where they are not aligned. So we can draw one like this and one like this. And that gives us two of our options for the px orbitals. Now, if we're looking at the py orbitals, which are going in and out of the board, I'm going to try to depict that, but a lobe would be going in towards you and one would be going back. So that means that we would have our line, same as before, and I'll just draw a shaded one going towards you, and I'll try to depict the unshaded one coming back. And that's what that's depicting here. It's difficult to draw in 3 dimensions, but I'm trying my best for you, and that's the same. And now we need to consider the other option where one is flipped. So one would be coming out at you, and then one would be going backwards. And in our other case, one would be coming out at you, and the shaded one would be coming backwards. So that's the same, just flipped. And now we need to consider the pz orbitals. So the pz orbitals are going to lie along the internuclear axis. So if we had the shaded regions both pointing in, that would look like this. And if we had them not both looking in, and instead they were flipped, then we would have a situation that looked like this. All right. So that is basically all the different ways that the py, the px, the py, and the pz orbitals can orient in space. And now we just need to consider the s orbitals. So the s orbitals could be both in the same phase, or they could be one in the positive phase and one in the negative phase. And basically that gives us all of our group orbitals with which we can make bonding interactions in CO2 for our group orbitals. So now what we need to do is assign which of these irreducible representations they correspond to, and then match them up with the center atom. And the center atom is easy because we know that an s orbital is always the top row, so the Ag is always going to be the s orbital for carbon. And then we can use the linear column to determine what the pz, the py, and the px are, which correspond to the b1u, b2u, and b3u, respectively. So we only have to do this for the outer atoms. So we need to determine which irreducible representation corresponds to each of these. So remember, the internuclear axis is the z-axis. So the first thing to do, since identity is positive 1 for all of them, we can just move on to the C2. So if we did a C2 rotation here, we would see that this would the phases would invert, and therefore I know that this is going to be some B symbol. And that's what the B tells you for the irreducible representations, is that you get inversion of the symmetry upon rotation around the principal rotation axis. All right, so I know that it's for sure not AG or AU, so that leaves behind 6 other ones. So systematically, we can go through. Again, the BY is going to be the one going in and out, and if we do a rotation along the BY, that gets us to a inversion as well, where all the positive phases or all the shaded regions end up being unshaded upon rotation. So that's a -1 for the C2Y. So that tells me that that I have a situation where I not only have a negative value for the C2, but I also have a negative value for the C2 in the Y direction. So now if we go, that basically leaves only 1, 2, 3, 4 with which this can possibly be. And then if we move to the C2 and the x-axis, which again is going straight up and down, we see that that one is a +1. So that means that it's either going to be that basically our only option then, because this other value was a -1, we still have between B3G and B3U. Now, if we go to inversion, we see that those are different. And if we were to do an inversion here, we would get a -1 value, which tells me that this is a B3U. And then your task is to identify which of these irreducible representations would correspond to these different group orbitals, following through in the same systematic way and assigning irreducible representations to each of these. So if you had walked through that process for each of these group orbitals, you would have assigned them exactly as I've done here on the screen. And now what we need to do is match the group molecular orbitals with the center atom corresponding to their irreducible representations. So remember that AG is always going to be the s orbital on the center atom, and we see that that one can make a bond with both the pz orbitals pointing in and the two s orbitals. At least from symmetry-wise, we could have the AG corresponding to both of those. Don't forget, though, you will need to consider energy as well. The next one, I go down systematically and see that B1U corresponds to the PZ orbital. So the PZ orbital on the center atom corresponds to the B1U. And I notice that I have also two additional opportunities to make bonding interactions with the B1U orbitals. And then I go to the PY and see that that corresponds to the B2U. So the PY is going to be the one going in the board and out of the board, which I'm trying to draw in 3 dimensions, which is kind of difficult. But assume that one of the lobes is coming out at you and one is coming back into the screen. So then that I see I can make a bonding interaction in here. And in fact, that's probably going to be the one that gives us one of our pi bonds, right? Because we know that in CO2 we have a couple of pi bonds. The next one is going to be the PX orbital, which is going to be the B3U. So the B3U on the center atom corresponds to the PX orbital. And as I can see, I have a B3U, and again, it looks like it matches up with pi symmetry. So I can already start to see how my molecular orbital diagram is going to look and how it should match what my Lewis structure looks like. So now let's take this and start to actually build our molecular orbital diagram by matching these center atom irreducible representations to their corresponding group orbital irreducible representations. So on our energy diagram, we have our carbon atom, which is the center, followed by our 2 oxygen atoms, which are the group orbitals. And we know that there are the s and the 3p orbitals possible for carbon, but those actually correspond to these irreducible representations. So I'm just going to write those here. So we have the Ag, we have a B1U, we have a B2U, and a B3U. On the outer atoms, we can make them up based on these, where the lowest in energy are going to be the s orbitals that are very low in energy. In fact, so low in energy that they're not going to interact with the Ag orbital from, or even the B1U orbital from the outer atom, from the center atom. So we have our Ag and our B1U, and that corresponds to these groups here. So we have used all of those. Our next B1U is going to be this one here. We know also that we have the Ag orbital. That is right there. We have our B3G orbital. We have our B2U orbital, our B2G, and our B3U. And basically all of those can be thought of as being very similar in energy. In fact, the ones where like this, for example, the B1U is going to be a little bit higher. So, in reality, it may be just right here when looking at the overlap and the orientation of the axis. Same for the B2G. But for our purposes, not super important. As I mentioned, and as you saw on the screen previously, these orbitals are going to be far too low in energy because the s orbitals of oxygen are too low in energy to interact here, which means that the only interaction is going to come from this Ag orbital on the outer atoms with this Ag orbital on the center atom. So we can make our first sigma bond by combining those two orbitals. And don't forget, you also need to make the corresponding anti-bonding orbital. And then from there, we can move on to looking at our B1U. So our B1U is here. And we see that we do have a B1U here, but again, it's too low in energy to interact, which means that I need to interact with this orbital because it matches the symmetry and the energy levels. So we have our B1U, which this is also making a sigma bond. So we have our second sigma bond, which we know we should need according to our Lewis dot structure. This is going to give us our second orbital. The next one is the B2U, and the B2U is here, which matches via a pi symmetry. So that's going to be our first pi interaction. And the B3U is also another pi interaction. So now we've used our B2U and our B3U, and those are basically the exact same energy, and they give rise to those two pi bonds that are formed here. So now we've used all of our interactions coming from the center atom, and we have matched them to the appropriate group orbitals. Now we see that we have 1, 2, 3, 4 remaining orbitals that have never interacted with the center atom. And that is actually going to give rise, those are 2 right there. That means we've used these 2. And we have the B3G and the B2G left to go. So I will bring those over and make, again, non-bonding interactions. So those are non-bonding. These are also non-bonding. We know that CO2 has 4 plus 12 is 16 total electrons with which we can populate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now we begin to populate our molecular orbital diagram, and we see that that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And notice that that places 4 electrons in non-bonding orbitals there and 4 there. That's a total of 8. And in our Lewis dot structure, we have 8 lone pair electrons, which are accounted for. We have 2 sigma bonds, which matches our Lewis structure, and we have 2 pi bonds, which again matches our Lewis structure. And this is how you can use symmetry and group orbital to create your molecular orbital diagrams for more complicated molecules. And we'll do some more examples of this in class.